All right. Now here's where we came up with our two residuals for our first two kids. Now if you go back to your list, go to Stat Edit, so you see your L1, you see your L2, go to L3 and go up to it and press Enter so that you can type a command up here. All right. Now I'm going to take a picture real quick so that I can write a little bit bigger with what all of this is really saying. Okay, this is what I want you to type in. L2, which you could press second 2, minus, go back and find that Y1 command. The Y1 command, again, you had to go to press the variables button, scroll over to the Y variables, and then you should be right at function, and then just take the first one, Y1. And then after that, it is absolutely important that you put parenthesis and then put in L1 end parenthesis. And then press Enter. And then you will notice all of those residuals, it's going to do the math for all of those kids' residuals. So these first two numbers you should recognize as what we just did on the last slide. Okay? But let me go through and tell you what this is really saying here. The L3 is where we're going to store all our residuals. The L2, list 2, if you remember, that was these numbers here, the scores that the kids actually got on that test. Those are our actual Y values. Okay? And we're going to subtract away this. And here's what was really happening. We were taking our L1 values, which were our actual X values, and this command is basically saying, it's like if you remember Algebra 2, Algebra 1, when you would have like f of x equals x plus 1, and you would say, what's the value of f when x is 2? And it would look like this, and you'd say, well, f of 2 is equal to 3. It's that same type of thing. It's that instead of saying f of x, we're saying take your y1, which was your predictor, your regression line, and take all of these x values in list 1, plug them into the regression line, and figure out what predicted value you would get for y. So when this command in your calculator is going to take all those predicted values, subtract it away from the actual values, and there will be all of your residuals here in list 3. Now, we're going to take all of those residuals and we're going to make what's called a residual plot, a graph of all of our errors. And you might wonder, why in the world would we want to take all of our errors and look at them graphically? Well, there are some very important things that pop up, some special patterns that may appear that will let us know if our data is really following a linear relationship, or if it might be better modeled by something not linear. Okay, and again, for the most part in this class, we're going to be focusing on linear relationships. So if our data isn't really linear, then using a line for predictions for other values isn't really going to be a good fit. You'd be better off using some sort of curved relationship. All right, now to make your residual plot, and this is what we're going to practice in class actually doing by hand, but you're going to do it in the calculator. Go back to your stat plot. So that was your second y equals. And go to plot 1, reopen it back up, but instead of using L1 as your X list, or we still are going to use L1 as our X list, but instead of the Y list being L2, put L3 instead. Because what we're going to do is we're going to graph our explanatory variable, our X values, versus the residuals. So once you say L1 and L3 for your scatter plot, press graph, and then you're going to have to press zoom 9 so that it fits your data, and you should get a picture that looks like this. This is the way a residual plot will always look. Now let me clear some of this stuff off here. you're always going to have a vertical axis right here, and then you're always in the middle, or roughly in the middle, I know this is from the calculator, you're going to have the x-axis come out here. Okay? And instead of this being the y-axis, this is going to be basically your residual axis. Where this line right here is where you had no air, and everything up above it is when you had positive residuals, and anything below 0 is when you ended up with a negative residual. Okay, now what I could do is, let's go back and find some values that we had there. What was the value of our first residual? Or here, let's take our second residual, which was negative 9.598 for our second kid, who was 26 months old, and we had an error of nearly negative 10. So if you found where 10 was at exactly, and I don't know where it's at because my residual plot here, the axis isn't labeled, but you would go out to negative to 26 month old, which probably, based on all our data, let me jump back and take a look at it real quick. 26 months, I believe, was one of the older kids. Really, the only older kid was that 42-month-old. So now if I go back and look at my residual plot, that's this kid right here. Because there's the 42-month-old kid, and you can tell he's going to have a negative residual because he's below 0. So here's that 26-month-old kid, and this distance you would have to go down to be able to get to this point. That's that negative 9.5, I think it was 9.8, I don't remember, negative 9.5 something. That's how you would go and graph that particular point. Okay, and you would have to do that for all the residuals if you were going to do it by hand. All right, or the calculator is going to plot them all for you. Now some things to look out for. This is where you might see some patterns. Okay, now this is ultimately what we want to see, is this type, where here's our residual at 0 residual, no error, and notice this is labeled here. Let me zoom in, or let me take a picture of this and make it a little bit larger here for us. This is ideally what you want to see. Okay, you've got, notice how many points are above the 0 line and how many points are below the 0 line. It's roughly equal. You got about as many positive error as you do negative error. All right. And notice they're not too big or too small. They're all roughly in the same range and just scattered about here. This is what you want to see. Okay, if you saw a residual plot that looked like this, then your data would be best modeled by a linear relationship with our least squared regression line. It would be a good fit. It wouldn't be a better fit with like a curved relationship instead, let's say. All right, now does the residual plot have a curved pattern where you might see something like this? Okay, and I'll refer to this as like a frowny face, or you might see a smiley face pattern. Okay, if you see that in your residual plot, the data is not linear, and you shouldn't use your regression line, your least squared regression line, to make predictions with it, because it's not a good fit. Now another pattern you're going to look out for, besides the smiley face, frowny face, is this type of pattern. And notice at first your residuals for your smaller x values, the residuals are small positive or small negative, but as x increases, notice the residuals get bigger and bigger and bigger. You kind of see this fanning pattern, where almost like here this looks like a less than sign. You could also see it the other way around, where maybe at first you have very large residuals, but as x gets bigger and bigger, the residuals get smaller and smaller. So it almost looks more like a greater than sign in the end. Okay? Again, if you see that type of pattern in your residual plot, then again, with this particular kind where at first you want to minimize the amount of residual as possible. So the smaller the residual, the better you are at predicting the y value. So at first your predictions are pretty close, there's very little error, but the more and more you go out and increase your x, the bigger and bigger your error is getting, and your prediction isn't as close as what it should be. For 4, look for individual points with large residuals. If you see, like we went back up here, let me make this bigger again. Let's say your residual plot looks something like this, and then you had this point way up here. Or maybe you have a point that's way down here. Something that doesn't follow how everything else looks like. Those are probably going to be outliers. Okay? Just keep an eye out for those. They may or may not affect your overall regression model. And we'll talk about that later. Look for individual points that are extreme in the x direction. Okay, so let's say most of your data, again, let's look at this. Say here's most of your values here, most of your residuals, and then let's say, put that there, you've got this one person way down here. And they may be right on the 0 line. You could have a person that's way up here, a large residual, but you've got most people clustered around a central area, and then way on later, this is like the 42-month-old kid who finally said his first word. He's probably going to be an outlier, or what we're going to call later an influential point. Okay, just that one kid's going to throw off potentially your predictions for other kids. So you may decide later to eliminate that kid. We're not going to kill the kid, okay? That'd be just wrong. We're not going to kill him, but we're just going to, kind of take a blind eye to that data point because it's not falling in line with everyone else, okay? So you may or may not eliminate a data point based on if you think it's really going to be an outlier or not. Okay, so again, those points with large residuals, we're going to call them influential points or observations because they're going to pull the regression line towards them. And if you eliminate that kid, then the regression line is going to bounce up or down depending on where that outlier was. If it had a very large negative residual, then that line's going to bounce up once you get rid of that outlier. Or if you had a very large residual, your regression line is going to get pulled up towards it, and once you get rid of that outlier kid, then that line's going to shoot back down and fall in line with all your other points. Okay, so let me show you this example here. Let me see here. So child 18 is an influential observation. Without child 18, the least squared regression line is drastically changed. So at first, when we had child 18 in here, this was our 42-month-old kid right here. Okay, notice your age at first word months. Here's 40. There's about 42. So here's originally the regression line, this solid line right here, if I can highlight it right. And then if we get rid of child 18, we say, let's pretend he's not really there, then here's where the regression line ends up at this dashed line. Notice it goes up. It doesn't feel like it moves up a lot, but that really is a big difference there. Now, if the regression line looked more like that, where it just changed very slightly, then maybe child 18 wasn't an influential observation. Okay. Now, the only way you're going to know if it really changes is if you go into your data set, into L1 and L2, and you eliminate the x and the y the x and y values for that specific influential observation, and then re-look at the scatter plot. or relook at the regression line. And you could even look at your correlation value. Did it increase? Now, the residuals will always add up to 0, just like when we did standard deviation. And I said, if you took all those deviations from every x value from their mean, and some were positive and some were negative, we couldn't take the average of those because the sum of them ended up being 0. So the same thing applies with the residuals. All of these positives are going to cancel out with all of these negatives in the end.